My name is Thorsten Chlupp. I'm the owner and president of RENA and Arctic Sun. Thanks so much for coming out. This is the third session of our summer educational series, which we put on just to put a little bit more information about renewable energy in Alaska in general and some of the things that can work in our climate. We've done a lot of research, a lot of experimentation over the last 6-7 years on high-efficiency buildings and renewable energy systems. And today we're going to talk about off-grid power, energy solutions for the last frontier. I'm going to just give a broad brushstroke of my opinion about really important things to remember on off-grid systems. That's much more challenging than being on an electrical grid. And then Nathan will take over and really go into the nuts and bolts on some of the systems, battery storages, and systems which can be used. With all that, when we wrap up, we will be available for questions. We're going to have plenty of time for Q&A sessions at the end of this. And if you have a little bit more detailed question or want some more information about some of the stuff we do, you can find us outside, maybe buy us a beer, get some free consulting. So with that, let's get started. This works. Let's see. Okay, when you're off-grid in Alaska, you're on your own. That's basically the short of it. It's very challenging to be off-grid in a normal climate. In our very extreme climate, being off-grid is very challenging. We have a tremendous amount of energy we require in the wintertime for heating, domestic hot water, plus the electric load, of course. So I don't have to tell you guys, this is reality for us. There's one thing we can count on in Fairbanks, and this is pretty much ice fog and really cold temperatures in the dead of winter. And this is unfortunately the time when renewable energy is a little bit challenging. So there's, especially off-grid systems, there's definitely huge challenges to overcome. 2 months out of the year we have almost no sun where we can get really energy from renewable energies. Wind is not such a great resource in Fairbanks. There are some sites which make sense, but overall we are not blessed with winds like you see in Delta or in other regions here. This is one of our most public off-grid houses we've done in 2009. This is called Castle's House. That was really one of our first attempts to build a zero-energy building in Alaska. And on top of this is off-grid, basically. So there is, in my opinion at least, way more to be said about being zero-energy when you're off-grid versus on-grid, where you can cheat and use the electrical system basically as your storage battery. Versus here, you have to produce on-site everything you require, really. For systems like this, we really developed these micro-hybrid energy systems where we are trying to combine renewable energies, some wood, high-efficient wood heat, and a buffer tank, big buffer tank storage, heat storage tanks to make up basically for the energy requirements. So really, I believe, specifically in an off-grid application, we need to look at biomass systems, at high-efficient wood-burning devices. Dan Gibbons, the builder of this beautiful masonry heater, sits over here somewhere. So grab him and tag him for information when you're interested in this. We're very, very fortunate to have him in town. He does beautiful work and he does very, very efficient heaters, and I'm a huge fan, obviously. This is all his work here on these slides. A masonry heater can provide a lot more BTUs, a lot more efficient heat in the building. By now we combine it also with the domestic hot water, and they work really well in high efficient buildings. And I can't stress enough, if you're really looking into building something off-grid, to look into high efficient wood burning devices. This is one solution. There's other ones of course available too, but I'm always a big believer in going local, using local resources, and keeping the money in our community. And we have plenty of materials available local, and we have some people here in town who can really build wonderful stoves. So in combination with the wood heat, we use solar thermal also, mainly to store heat, basically for heating and domestic hot water. This is a small 6-panel system for the combined heating and domestic hot water with a combined 2,500 gallon heat storage tank. To the left you kind of see the little bit of plumbing that all requires to get you a pretty good system, and this runs on very low energy requirements, so very attractive for being off-grid. That's the typical inside of one of our tanks: solar stratifier, domestic hot water coil, and the wood and the solar thermal both tie into the system, so we can always in the wintertime too, when there is no sun, utilize the same system, maximize efficiency, and get the lowest energy input we require to get the most out. On Carl's house, on our first big experiments as far as annual heat storage, we had a massive tank, 12,000 gallons. We installed quite a few more of these big tanks by now and really improved the systems. But something, if you want to live off-grid in a harsh environment like this is something to look into, something to consider, besides all of the electrical requirements, which is really the main focus of our talk today of off-grid, which Nathan will take over here in a minute. So with that, what technologies are out there? How can we make this all work in the dead of winter when it's really cold? And what are the challenges? What are the technologies? That's kind of the overview we want to give here. And with that, I'm going to hand over to Nathan, who will go into further detail.
Hi there. It's great to have you all here, and we're going to dive right into some of the specifics of the technology that's available. So this right here is a diagram of many of the possible components you would have in an off-grid electric system. The heart of any off-grid electric system is going to be the storage, and right now that basically is going to mean a battery bank. We'll talk in the rest of the presentation about some different potential options for storage, but in terms of having readily available electricity, the battery bank is what we have as an option right now. Another important part of any off-grid system is going to be an inverter. So a battery provides DC electricity, which is useful for many things and less useful for many others. An inverter, the main function of an inverter is to take a DC energy source, in this case a battery bank, and convert that into usable AC electricity. AC electricity just like we get off the grid. That's the main function of an inverter. Often, and in an off-grid system, we're going to have renewable energy sources, as Thorsten alluded to. In this case, here we have a PV array, a solar electric array. A part of any off-grid system is going to be a way to control the charge, a charge controller here. That's a safety feature to prevent overcharge of a battery bank. It also can have many other functions, and we'll talk in some depth about the options there. In a typical off-grid system, especially here, a generator is going to often be required if you want continuous power through the winter, if you want a healthy battery bank. We won't talk too much about generators today. We're kind of talking specifically about renewable energy sources today. But a generator is most frequently a very important part of an off-grid system, and I'm happy to answer any questions you have at the end about that. There's some other things we may look at in an off-grid system. Different types of meters and monitoring devices to get us a status of how our system is operating. It's a little different than the grid when we really don't think about the amount of power that's there. We don't have to worry at night whether when we wake up in the morning whether there's going to be power available to do the things we want. In the off-grid system, having a really firm grasp of exactly what's happening is a critical component of it. Another thing about off-grid systems is we talked about how you have a DC source of electricity in a battery bank. It's quite common to run DC loads in an off-grid situation. A pretty common scenario would be a small 12-volt system that you'd have at a cabin. And there's many DC loads that you could possibly run in that house directly off a battery bank. Anything you can run in a car is most likely a 12-volt DC thing. So a car radio, for example, different 12-volt lighting, those are all options. For the rest of the standard electronics, that's all AC, so that's where the inverter comes in. This gets to be kind of an interesting scenario when the end product, what we're looking for, is actually DC. A good example is a battery charger, right? Where we're essentially in that scenario drawing DC electricity off of a battery bank, converting it to AC through an inverter, and then plugging it into a wall where it's directly changed again into DC electricity. A pretty inefficient process overall, but it's what we have at the moment. So we'll talk in some details about some of the equipment coming up. But one thing to really keep in mind when we're looking at off-grid systems is, like I said, grid service, we kind of take it for granted. It's, a 200 amp service is totally common now. Most houses probably go ahead and get a 200 amp service. If we want to think about how much power that actually is and what it would take to replicate that type of service off-grid, it's an enormous system. This is an enormous and very, very expensive system to provide 200 amp, the equivalent 200 amp service. We're talking, 6 state-of-the-art large inverters. Possibly you could do it with a different, any different configurations. But the bottom line is this is an incredibly expensive way to go. When we start to think about off-grid, we first off really need to take a whole different approach to looking at where our electricity comes from, how much of it we're going to use, because you're going to be intimately involved in where it comes from. So again, what was standard and easy on-grid, definitely not necessarily so off-grid. I'm going to talk really about the specifics of the equipment, and later on we'll get into a closer look at the load side of the equation. So we said an inverter was going to be an important part of a system. Again, the inverter takes DC electricity, typically from a battery bank, and converts it to AC. There's any number of different sizes, styles, qualities of inverters. Here we just see a few things. This is straight off the internet from someone who's offering schematics for a build-it-yourself inverter. We got here some questionable brand inverter from, we'll talk about power quality issues in a moment. And then, down at the bottom, this would be more of a real top-of-the-line system that you could use to run a whole house. So in terms of different types of inverters, one thing we're going to focus on here for a second is the quality of the power, the type of waveform that that inverter can deliver. Here we see a comparison of a few different types of inverters you could see. First off, AC electricity, when you get it off the grid, the idealized form is a sine wave. Nice and smooth right there. That's the idealized form of what that wave looks like when we look at it with a meter, with a scope. So a good quality inverter most likely will be able to come very, very, very close to mimicking that idealized waveform. Another type of inverter might be what you might see it as a modified sine. In truth, that's a lot closer of a waveform to what's called a square wave. You see here, it's essentially, if this is the axis of time, this is voltage. So the way a square wave works is it's basically full power, positive, full power, negative, full power, positive, full power, negative, back and forth like that. It's not what you'd call a clean waveform, but for certain applications it's acceptable. Kind of somewhere in the middle here is what they're calling a modified sine wave. So that's kind of an attempt to get it closer to the sine wave. What does this mean in terms of for what you need for your particular system? Well, it really depends on what you're trying to power. Here in our business at Arctic Sun, when people come and ask us, what type of inverter do you recommend, we hands down always recommend a sine wave inverter. And that may not have been a firm recommendation as little as 10, 15 years ago. The bottom line is that power quality is every day more and more and more important. We all have many different types of sensitive electronic equipment in our lives that require on this clean sine wave type waveform. They just won't work off a square wave. So, you can get cheap square wave or modified sine wave inverters. We don't typically recommend them just because you may save a little money on the inverter, but unless you're very careful, there's a decent chance you can burn up some equipment. Another question that I hear in the shop all the time is about about voltage and about what type of an inverter should I have. Should I have a 12 volt inverter or a 48 volt inverter? What's the benefits of upgrading my existing 12 volt inverter? So when we're talking about 12 volt, 24 volt, 48 volt, that's the nominal voltage of the whole system. That's basically the shorthand way we're describing what we're actually describing is the number of cells in the battery bank. We'll get to that in a minute, but for now, it's basically showing what voltage the battery bank operates at. The inverter's job is to take that power and turn it into AC. It's going to be either a 12 volt inverter, meaning it's basically compatible with a 12 volt bank. So when people ask me that question, what's best? And again, this is opinion, and there's going to be many different cases, but a lot of it comes down to what are you trying to do? Do you already own the thing? That's a pretty common answer is, well, if you already own a 12 volt inverter, that's a pretty good reason to stick with it. If you're starting from scratch, we always recommend steering into the higher voltage. And the reason is tied up here in our middle school physics class, if you can remember. This is Ohm's law represented in a graphical function. And the one we're going to focus in on is this. It's a representation of power. So how that translates is to efficiency of transmission. And this is an equation that's handy to represent potential loss in a system. So here, what this equation really practically means is that for the fixed amount of power, that's the power, right? On the same cable, this is R stands for resistance. Electricity flows more easily through less resistance. So we're representing a fixed amount of resistance here by saying the same cable. We have a cable of a certain size, of a certain length, that has an amount of resistance. So if we're going to transmit the same amount of power through the same cable, this is what's going to influence our transmission losses. And here's an example. If we're transmitting 3,000 watts over a very large cable, a 4-aught cable, that's a big expensive cable, and our distance is 15 foot. If we look at the amount of energy that's lost just in that cable, this isn't inefficiencies in an inverter, this isn't inefficiencies in an appliance, this is just energy that's lost to heat in the actual wire. Going from 12 volt to 48 volt translates to it's a squared function, so when we double the voltage, there's 4 times less loss in that line. So you can see right here, in this case, if this is what we're doing, there's tremendous efficiency advantages in operating a 48 volt system versus a 12 volt system. And that trickles to every single wire in our system. When we build these systems, there's lots of different wiring we have to look at. If this is the case every time, those losses really add up. Bottom line is that for a very, very small system where we're actually transmitting a small amount of power, a 12-volt system may be appropriate, and that may be the best choice. For any system of any serious size, there's always many, many, many gains to be made by looking at a higher voltage system. So let's move on here and talk about another part of the system we're going to have, and that's energy storage. Here is showing a rather much, much larger size storage system than would be probably appropriate for a typical residence. This is here in town, and I'll just take a minute to mention that we have been asked by ACEP to partner with them in a series of lectures coming up, or I guess at least one coming up, so look out for that in the future. They give a great series of talks here throughout the winter, and we're looking forward to working with them. Like I said before, kind of the best, storage is a really tricky thing. To be honest, it's sort of like we're looking at the least worst option at this point. It's not perfect. Batteries are expensive. They're heavy and can, as we'll talk about in the future, pose some safety hazards. It's really the technology that's available for most of us today. There are other options, and we'll touch on them. So let's talk first about a couple different types of batteries, a few different battery technologies that you'll see. So this is what's called an AGM battery. You'll hear it referred to as a sealed battery. AGM stands for absorbed glass mat. This is a type of battery, maybe you've heard it called maintenance-free. Some people call it maintenance-free. Another pretty applicable term would be unmaintainable. So this is a potential type of battery you could use in your system. It's going to have some different advantages and disadvantages. Bottom line is that this is really when we would typically recommend it. For most people, all else being equal, you get a better bang for your buck from what's called a flooded battery. So the difference between the two is basically a flooded battery is filled with a liquid electrolyte. An AGM battery is also filled with a liquid electrolyte, but none of it is, all of it is absorbed in these fiberglass bats that exist between the battery plates. If you get a crack in one of these, if you actually puncture a hole in it, there's no fluid that'll leak out. All of that fluid is held in the AGM, so there's some safety advantages here. Whereas with the flooded battery, it's a different type of chemistry, and it's a different whole maintenance regimen. Part of dealing with a flooded battery is problems from hydrogen off-gassing. We'll talk about battery safety in more depth, but part of the normal charging and discharge cycle with a flooded battery is that the one byproduct that comes out of that is hydrogen gas, and as we know, that's a potentially dangerous thing if it's built up into too high concentration. It can be explosive. So, one thing is that we always need these in a dedicated, sealed utility space. A flooded battery bank needs to be vented, needs to have the ability to trap that hydrogen gas and vent it to the outside and keep it away from potential fire hazard. In general, these are kind of the two most common types of batteries you'll see. They're both what's called a deep cycle battery. A deep cycle battery is a different type of battery than what you have in your car. In your car, that's called a starter battery, and it has a very different function. A starter battery, its job is to provide a lot of current for a few seconds to get your engine started. After that, its job is basically done. You have an alternator in the car that takes care of all your electrical needs. That battery, what it's got to do is for just a few short seconds to deliver a massive amount of current. A deep cycle battery, on the other hand, has a very different function. its job is to deliver less current over a longer amount of time. In a starter application, in your car, typically we're only really cycling the top 1 or 2% of the actual energy that's in that battery. It's got many plates, they're closely packed together. It gives a ton of current for a very short amount of time. We're just cycling that top bit. A deep cycle battery has fewer, thicker plates, can deliver less current at once, but we can use much more of the battery by essentially being able to cycle the battery through a larger percentage of it. So those are the two main types of batteries you'll be encountered, and each of them has its application. You really have to look at your own individual case to decide what's going to be the correct application for you. So let's talk about a few general things about battery life, battery performance, and some of the expectations we can get when we're thinking about purchasing a battery bank. The next three slides are all charts from the Concord Battery Company. That's one specific brand of batteries. But the principle applies equally across any different number of batteries. So, if you're looking at a different battery, it very well may have different numbers, but the curves essentially all look the same. So the first thing here we can look at, this is a chart that's showing how many expected cycles of a battery, basically how many charge cycles, how many times do I bring it down and bring it back up to full charge. How many times can I do that until the battery essentially has no more useful life? And this chart shows basically the average depth of discharge. So if 0% is a 100% fully charged battery, right? And then we're looking down the chart. So if we use the top 10% of the energy available, that's here on the chart. If we discharge it very deeply, and if we use all of the energy, we may be cycling it down into the bottom range of it. What this chart tells us is that the number one thing that's going to influence the life of a battery is how deep we discharge it. And it's real simple. The less of the battery we use, the longer it's going to last. The shallower we cycle it, the more we can expect out of a life. And if you look at this is something you got to realize, this is not a linear graph, right? So it may look like this is a pretty flat curve, but that's actually a logarithmic scale. So if we wanted to look at it really, the graph would be, I think they do it this way because the graph would be very, 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 very tall if you didn't have it on a logarithmic scale there. So that the way that curve actually looks, if we're kind of comparing it, in a straight line to a straight line, it would look very, 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 very steep. So this is a quandary you'll face if you ever are operating an off-grid system, and maybe you may have a renewable energy source like solar or wind that in that case the fuel is free. You're not paying for the fuel source, so you don't care as much how deep. How much of that energy you're going to use. Let's look, on the other hand, at if you're essentially charging your batteries off a generator, there's always a little bit of a conflict of interest here where it's, on one hand, we want to be able to use more of the battery because that's going to allow us to run a generator more efficiently and burn less fuel. On the other hand, we want to use only a very, a lesser amount of the battery because we want the batteries to be able to cycle more and to last a much longer time. So that's always a little bit of a conflict, and again, you're going to have to kind of weigh the costs and benefits yourself. Typically, in an off-grid home, we find somewhat of a compromise. Another influence on the performance of a battery bank and also the life of a battery bank is the temperature. So this graph shows the temperature of the battery bank in Celsius versus the available capacity. And what this clearly shows is that the colder it is, the less energy that's available to us in the battery. Basically, the colder a battery is, the less energy it's going to be able to store. Up here we can see, as we get hotter, the performance, the available energy that we can take out of a battery increases. The other side of this equation is that there's a very, very similar curve. It basically mirrors this exactly, and that's life expectancy of a battery versus temperature. And in that case, it's the exact opposite. The colder a battery is, the longer it will last. The hotter a battery is, though it's performing better, the chemistry of it, the plates, all the parts degrade faster, and we'll have the possibility of premature failure is greater the hotter we're cycling a battery. Again, on one hand, having the hotter battery bank allows you to use more of it, gives you an increased capacity, but it's going to shorten the life. So again, it's kind of weighing the costs and the benefits. If you keep your batteries too cold, it essentially reduces the size of it, and you may end up burning more fuel from that way. Whereas, if you keep them too hot, you get better performance, but reduced life. You're going to have to weigh all those things out. Typically, it's finding a middle ground, finding a compromise. Not too hot, not too cold. So we talk a lot about capacity, right? Capacity simply is the amount of energy that's available in there. Well, that's not, in addition to some of the other issues we talked about, that's not always as easy as it sounds. So capacity for a battery, there's not a fixed amount of capacity. Capacity is also influenced by essentially the amount of current, the amount of energy we draw it out, the rate of change. So what this shows here is essentially showing this is the depth of discharge. So this is showing, we're starting with a full bank and going down to a nearly empty bank. And each of these lines represents the same battery, but essentially discharging it at progressively slower rates. So when you're buying a battery, you'll see something called the C rating. Here, this is the percent of the C24 rating. What that means, C24 in this case, is if you have a battery and you discharge it over 24 hours, in this case, the total amount of energy that's available to you, that's the C24 rating. So we can see from here that if we, 24-hour rating is right there. So that's basically, how much total energy is available to us if we do a relatively slow discharge. Now let's say we have a different application with a much larger load, and we're not going to slowly discharge that battery over 24 full hours, but we're going to discharge it over only 1 hour. From this chart, we can see that the difference is really dramatic. It's nearly 50% less capacity if I use that energy in 1 hour versus if I use it in 24 hours. So this is something to really pay attention to when you buy a battery. A battery is going to be rated capacity-wise by the number of amp hours. An amp hour is basically a unit of capacity. It's 1 amp times 1 hour. So 100 amp hours. You may find a battery that's 100 amp hours. What does that mean? That means 100 amps over 1 hour, or 20 amps over 5 hours, or 1 amp over 100 hours. If you see a battery and it says it's a 100 amp hour battery, well, that's pretty meaningless in and of itself. Is that 100 amp hours, discharged over 1 hour or over 100 hour? The standard is 20 or 24 hours. That's, probably you could trust that if you see a battery and it says it's 100 amp hour, that probably refers to either a 20-hour rating or a 24-hour rating. Someone who's maybe trying to sell you more battery than what it actually is may say this is 100 amp hour, and you go to look at the fine print and find out that's actually at the 100-hour rating. That 100 amp hour battery at the 100-hour rating is in fact much smaller. So when you're comparing apples to apples, you really got to make sure you're looking at the same type of a rating. So one thing I stress in the shop when people come in is the ability to monitor a battery bank, to meter how much energy is in your battery. These are a number of different options. I mean, they range from simple analog voltage meters and up. Some of these are really sophisticated computers, basically. The importance of this is that, like we talked about in an earlier slide, battery capacity is critical to long-term health. If you're consistently drawing a battery down 80% of it, you're going to get a drastically reduced life. Having a good quality battery meter of some type will allow you to be informed about exactly how much energy you're using out of your battery bank and enable you to get a charging regimen that will lead to longer, healthier batteries. So, battery is kind of what we have at the moment. There's some other possible ways we could store energy that are very exciting, but somewhat less commercially available here. This is one that we talk a lot about in our shop, and we think could be tremendous potential for us here in Alaska. This is hydrogen storage. So the simple concept is here when we have all this energy in the summer, right? To store it effectively in a lead-acid battery would be tremendously expensive, tremendously inefficient. Well, what if we could, instead of storing that in a battery, make hydrogen fuel? So we have extra solar energy. We make hydrogen fuel, store it, and then come winter, we have that solar energy all stored up and ready to use for various different things. It could be to power your car. Could be to power a generator to make electricity, any number of different things. So there's really very few, none that I know of, small-scale solutions that would make this a reality right today. But there's some really exciting research going on. That one especially, kind of a prototype project happening presently in MIT that we're following closely. And it could hold a tremendous amount of potential. Storage is such a tricky thing. A lead-acid battery really is, it does a great job day to day, maybe over a couple days, much longer than that, and it's just not a practical solution. This could really make effective solar energy storage a reality for us here, that we could take full advantage of these long summer days and use that energy deep into the winter. So let's shift gears here and talk about some different sources of energy. We talked about the inverters, what we're doing with the energy, some storage mechanisms, some renewable energy options that are going to be great additions to the system are solar energy here. This is a solar electric system, an off-grid solar electric system. We'll talk about wind in a minute. Whenever we talk about PV, photovoltaics, solar electric, solar panel, we also, the companion topic is going to be on charge controller. Here's a number of different charge controller options, ranging from a very small one that would handle one module of this size, up through this controller here, which is kind of state-of-the-art. That's actually the controller that's controlling this entire array. So this entire array is being controlled by this controller right here. This is a graphical representation of the way a PV panel produces power. This shows basically the full operation. So on this one axis here we have current, and here we have voltage. This yellow curve represents the line that a PV panel, when you connect a load to it, somewhere along that line, it's going to operate. That's going to be the point on that curve where it operates. On one end, we have zero voltage and high current. On the other end, we have maximum voltage and no current. This is called open circuit. This is called short circuit. The important takeaway here is that for any curve, there's always exactly one point which is called the maximum power point, and that is defined as the point on that curve where we can extract the maximum amount of energy. Energy is going to be current times voltage. So this point, right, if we move up this line, we have a higher current, but we're losing voltage. If we move down this line, we have a slightly higher voltage, but much less current. There's always one point called the maximum power point. This plays into the type of controller we're going to choose, and we'll just jump right into an example, and I think hopefully that will illustrate what I'm trying to get at here. So this is the real life spec sheet of a solar panel. It's being advertised today here in our state as a 24 volt solar module. That's right in the ad. And part of our educational prerogative here, we think, is to point out some misinformation out there. And I want to show why this panel in particular is not a 24 volt solar module. The thing about voltage to remember is that we're always first talking about nominal voltage. So a 12 volt nominal battery, right? Like the one in your car. We call it a 12 volt battery. It's probably, if we put a meter on each of our cars, we'd read somewhere between maybe 13.5 for a weak battery up through 14 volt for a stronger battery. When we are actually charging it, that's going to be higher than that, 14.5, 15 volt maybe. And your alternator may hum along even higher than that. So 12 volt nominal is exactly that. It's how we refer to it, but it has nothing really to do with the actual characteristics of how we want to charge it. So a 24 volt battery, if we had built a battery bank and was 24 volt, depending on chemistry, we're going to charge it at a certain voltage. For a flooded battery, that's probably something like 28.8 volts. 29 volts, let's call it. So it's a 24 volt nominal, but we want to charge that battery at 29 volts. Well, here we see our voltage of the maximum power, and that's the voltage at this point, is 29.6 volts. Well, on first blush, we think, okay, that's reasonable. That should be able to charge a 24 volt bank. I want to charge my bank at 28.8, and I got 29.6. Well, we got to look a little closer than that. There's another big influence on the way that PV works, and that's temperature. So, you may be familiar with, there's a lot of talk about here, and I always tell people about how amazing it is to watch some of these PV systems work in the springtime up here. A nice, clear, cold, bright, sunny day in spring. It's incredible. I'd go around and test systems, and I've seen PV systems operating easily at 130, 135% of their rating. So that's 35% above what the factory tells you it should on a nice, clear, cold spring day. So the cold temperature increases the performance of a PV panel. At the same time, hotter weather decreases it. Here's a graph. So this is basically that same curve we were looking at, different panel, but we can see here as the temperature increases, the performance just goes down, and the vast majority of the change in performance is in voltage. It's not in current. The current in a panel is pretty flat across a broad range of temperatures, whereas where voltage changes quite dramatically. So what does that mean for our alleged 24 volt panel here? Here we can see the temperature coefficient of the maximum power, half of 1% per degree Celsius. Bottom line is that where, let's say that maximum power point was here, 29 volts. As we can see from this slide, in hot temperatures, this curve is going to actually scoot way back. So that maximum power point at a hotter temperature is going to be, could be closer to 25 volts, significantly below where we want to actually be charging a 24 volt bank. So here's some recommendations for a 24 volt system. we actually want a significantly higher voltage window, and that's because of temperature. Temperature, you have to take that into account. If it only were cold, that's a perfectly fine 24-volt panel. In the spring and in the winter, for all practical purposes, we can say, yes, go ahead, that's a great panel. But if you want to work in the summer, and if you want to work when it gets hot from being stuck in the sun, it's not at all a 24-volt panel. So we got to look at some of these details if we want good success with using solar energy. So we talked about the MPPT, right? The maximum power point. Can we use that panel, the panel that we said already was not a 24-volt panel, to charge a 24-volt bank? Well, the answer is yes, if we look at the correct kind of charge controller. So here, we're looking at a certain type of charge controller, an older style, a cheaper style. The way it basically works is that it takes a higher voltage from a PV panel. This is paraphrasing, this is not at all a technical description, but essentially, it takes that higher voltage, lops it off to match your battery voltage. So in that case, right, here's the curve of our PV panel. Right here, we got a 24 volt, 25 volt, whatever it is that we're charging our bank. That's where we're going to operate. There's all this energy that's left on the table. And the way we can make use of it is through maximum power point tracking. That's the type of controller that we typically recommend. A maximum power point tracking controller takes a higher voltage source. It has the ability to load the panel in such a way to find that maximum power point, that point on the performance curve where we'll be extracting the absolute maximum amount of energy, operated at that, and then essentially what happens is that extra voltage is transformed into extra current. So we have increased energy delivery to the battery. This chart kind of describes some of the benefits of the maximum power point tracker. It's not for every situation. Here we can see that we have all this energy on the table. Well, that's great if you can use it, but is it worth spending extra money if you already have enough energy? A battery bank can only be 100% full. It can't be 110% full. So at some point, let's say our battery bank is already full by noon because we have a large solar array, extra efficiency is maybe something you want to think twice about paying for just so you can have your battery bank full at 11:30 instead of noon. That's kind of up to you whether that's a good way to spend your money, but typically we would recommend looking at putting that money into some other way. That's certainly not the case. More often than not, you're looking for that extra energy. You can put that extra energy to good use. Maximum power point tracking is a great way to do that. Those controllers certainly do come with a higher price tag. Let's talk about wind power. Wind power is something, it's interesting, it's been around and harnessed for hundreds and hundreds more years than solar electric energy, but in a way has not come nearly as far in terms of maturity of the technology. Here's just a few different wind turbines. This would be a very small turbine that would be great for a little off-grid cabin. This is a much larger 10 kilowatt turbine. This is called a vertical axis wind turbine. And if you talk to me afterwards, I'll tell you why that's the last time I'll mention it in this program. There's a reason why for hundreds and hundreds and hundreds of years this design has proven to be of the best value, and why this is essentially snake oil. So in terms of wind, here's what you got to know about the power performance. We talked about some of the different issues with tracking power, maximum power point tracking in solar. With wind, there's three things that influence the power you're going to get. There's the density of the air, there's the swept area, the size of the wind turbine. By far, the most important thing is the velocity of the air, the wind speed. If you got wind, it's going to work. If you don't got wind, it doesn't stand a chance. It's a cubed function, right? So doubling the wind from 6 to 12, we got 27 times more potential energy. That's really the bottom line. If you have a good stiff wind, there's a ton of energy there and good ways to capture it. Wind's a tougher sell up here. Here in the Tanana Valley, we typically have, in most cases, just insufficient winds to really justify the use of a turbine. However, being off-grid, that's not necessarily the case. You'll notice from one of Thorsten's earlier slides, Carl Castle's house, the Sunset Roost, he has a wind turbine and it works really well for him. He's in a good spot. You know, there are a few pockets where there's good wind, good location. The other thing about wind that makes it particularly beneficial for off-grid systems up here is that it's a real source in the winter. You know, solar energy, highly, highly deficient in the summer months, as we all know. In general, we get better wind in the winter. In general, we have better wind at night. So it's an excellent complement to a solar system. Another nice thing about this is that if we were looking for a match for a solar, we actually get improved performance here by operating in colder temperatures. So this is looking at how dense air is versus the temperature. So we saw earlier that, you know, it's the smallest function, right? So this is the most important function. This is the second. This is half as useful as that one. Nevertheless, in terms of optimizing a system for having something in the winter, we get a little bit of a boost because of the denser air. We tend to talk a lot about solar because it's simpler, there's no moving parts, it's reliable, it's affordable, it's kind of a no-brainer. Wind, we talk a little bit less about in the shop because simply put, it's a little bit more of a complex machine. There's moving parts, there's maintenance required. You may just not have a good resource at all. Solar is very democratic in its distribution. You know, from here to the other side of town to anywhere in town really, barring any shading issues, the sun pretty much hits all of the Tanana Valley in a relatively equal manner. That is not at all the case with wind. You know, you could have a great site, your next door neighbor could have a terrible site. So really looking at your specifics is going to be the only way we can really know for sure. So I want to shift gears here a little bit and talk about some safety issues. And this is both from the point of view of if you were to install a system or just to be a homeowner. This is an electrical system. There are potential dangers. There are also, completely safe systems. When a system is installed correctly and when the operator has knowledge about what the different parts are, how it works, what the potential dangers are, it's as safe as any electrical system in your house. That said, there are certain things about the systems we talked about that are fundamentally different, that if you want to work on them, that if you want to live with, you need to know about. Solar energy, right, has a tremendous amount of potential. So this is sort of cheating because this is like not at all an off-grid system. This is a large commercial PV installation. But just to give you an idea of the potential power that's out there, this is a 4-inch steel pipe, steel conduit. And this is just, what poor installation practice can lead to. This burned a hole right through it, led to a fire on this roof. The potential is out there and it's real. So we talked a little bit before about DC and AC. This plays into the safety factor. So these are graphical, this is a graphical representation of the type of waveform. We set an AC wave source, looks like this. It crosses 0 here quite frequently. A DC source is constantly positive, or alternatively, constantly negative. What does this mean in terms of safety? Well, one thing is that there's a fundamental difference in the type of gear that you can use with DC systems versus AC systems. Do not go down to the Home Depot, buy a circuit breaker box, and hook it up to your DC system. It's a terrible idea. Here's the reason. AC crosses zero 120 times every second, right? We have a 60 hertz system here. What that means is 60 times a second, every single second, we get this complete waveform. 120 times every second, the actual current in an AC circuit is zero. There's no current 120 times every second. Let's look at a DC system. At every point in that same second, there's always DC current. There's always DC voltage. So in terms of when we construct a switch, for example, a DC switch, it's fundamentally different than when we're using an AC switch. AC is really easy to turn off. If you have a switch and you turn it off, all you have to do is wait for 1/120th of a second, and there's no current to turn off. An AC switch is made of, they're smaller, they're not as robust in their construction, they have fundamentally a simpler, easier job to do than a DC switch. So in general, when we look at comparing AC components to DC components, the DC component is going to have a higher construction standard. It's going to be able to essentially take more abuse. It's going to be just a more rugged, in every way, device. And that's, in terms of switching, that's exactly why. Let's talk a minute about battery safety. So, like we said, a battery was going to most likely be an integral part of every off-grid system we look at. That said, there are certain dangers and some certain potentials that we need to be aware of. Here's a case where a battery terminal has just completely melted away due to high heat. So batteries, they are not current limited. Remember that chart for the PV panel? And it showed that the maximum current from a PV panel was maybe 8 amps, and it ranged from 0 to 8. What that means is that no matter what we do, even if we put that thing in space, point it right at the sun, it's still only going to deliver 8.5 amps. It's current limited. That's just the maximum it can possibly deliver. A battery works fundamentally different. If we short circuit a battery, say by dropping your wrench, there is no theoretical limit, really, practically, to the theoretical limit of the amount of current that it can deliver is directly proportionate to the resistance across those two terminals. So 10,000 amp, 20,000 amp even, easily can be delivered in a split second when we short circuit a battery. So you drop your wrench, there's a serious potential for explosion. That's a tremendous amount of energy we're talking about. Another problem we really got to look at with batteries is high resistance terminals. So if we get a problem with a poorly corroded terminal that we've attached to a battery bank, possibly from rust, possibly from spilled battery acid, that creates more resistance, that hinders the flow of electricity through it, and the end result is that that's going to create heat. And that's exactly what is the most likely cause for this. It's a fire hazard. In addition, with a flooded battery like we talked about, that's going to produce, during the normal charge cycle, this is completely normal for it, during the normal charge cycle and discharge cycle, a flooded battery will produce hydrogen gas. So this is a little device you should consider if you're living with a flooded battery bank. This is a small powered vent. This is a little DC motor, so you run it direct off your battery bank. There's different control mechanisms, but essentially, as you're producing more gas, a controller will ramp up the energy to this fan and exhaust that hydrogen gas out of your building and keep you safe. Here's another potential hazard here, and this is one where when I make calls, when I do service calls, I often see potential dangers. So flexible cables are really, really popular, and they're convenient. They're a really good way, if you're in a tight battery box, to get a larger cable into what otherwise would be a very difficult spot. The problem with that is the reason why these cables are highly flexible is that instead of being made of a few larger strands of copper, they're made with many hundreds of very, very small strands of copper. One thing you'll see, and it's a terrible idea, is the use of this box lug. So imagine here, I can bolt that really easily to a battery terminal, and then I just shove the wire in there and screw it down. This is a really big recipe for disaster. This type of terminal is designed to use with a normally stranded wire, so a wire that has 7 or 27 strands. What happens when you put a finely stranded cable in there is that you'll crimp it down, you'll screw it down as hard as you possibly can, and then it's amazing. I've seen this happen. You go back even an hour later, and those fine strands just mold into place, create a loose terminal, create more resistance, and ultimately create heat. So what does that mean? If we want to use these cables, we really got to be careful. They're only to be used with the code. If we want to look at the code for guidance, with a listed type terminal, and those are invariably a crimp type terminal, right? So if you're going to use these, invest in a crimp tool, the correct crimp tool, or hire someone who has the correct crimp tool to put on the lug for you. Very, very important, and one of the most common safety issues I encounter. So in a battery bank room, what's some of the things we can do for protection? We talked about how battery acid is corrosive and potentially could be dangerous to yourself or to some of your property. So here's just a few things that in your battery bank room you'd want to have on hand for regular maintenance. This may seem a little funny at first, but this is a really simple, super cheap bit of insurance here. If you do happen to, during maintenance, spill some battery acid, baking soda is the perfect way to neutralize that. Basically, you have a box right there on hand, and in the event that you spill some battery acid in one way or another, put some baking soda on it and takes care of it right in a flash. So, kind of in conclusion about safety, this is something that as professionals we struggle with all the time, and sometimes these things are at odds with each other. On the one hand, we have kind of common sense safety, and on the other hand, we have compliance. And I think this illustrates my point exactly. This, for the record, this is not my wrench. But were it my wrench, you can see it's triple taped here with a good quality 3M Super 88 electrical tape. This is the good stuff, not the cheapo stuff. Is this a safe way to interact with a battery bank, right? The point here is that we've insulated the handle, so if someone were to accidentally drop this wrench, right, we may be able to touch one terminal, but we've insulated from the second terminal, preventing a short circuit. Is this safer? The answer very well may be yes. Is this compliant to OSHA standards? Absolutely not. In no way. Is it still a good idea? It very well could be, If you, are going to invest in an expensive set of insulated tools, power to you. If that's not for you, some common sense safety, something like this can go a long way. So I think with that, I'm going to turn it back over to Thorsten to kind of talk about the other side of the equation, which is we've talked a lot about how to make energy, how to store it. Now let's look about smart ways to use it in an off-grid situation.
So now comes the real boring part. I mean, we always want to stick up panels, stick up wind towers, and produce something. You want to dig deep in the ocean or somewhere up in the Arctic to get more oil so that we can burn bigger fires. But really the key answer, at least in my opinion, is not how do we build a bigger fire. It's about, how do we utilize a small fire and go a long way. If we burn this over a whole year, it keeps us warm versus burning it up all at one night. So loads, I think, are really important to understand and to really grasp and spend a lot of time on. I mean, that's really where most of my work is, analyzing, where are we really consuming, where can we increase efficiency, where we can make buildings function on a much lower level. Our key target on any new building we design is 80 to 90% reduction in energy. This is, on the whole approach of the building, basically. So reducing the loads, if we're looking at loads, in our climate, it's pretty obvious for everybody. Heating is a huge problem. The more we insulate buildings, the better buildings we build. Domestic hot water, since we're using it every day for 365 days out of the year, normally, becomes a bigger issue than heating. But overall, it's a huge load which we put on buildings. And then, of course, we have electricity. And in all of these systems, efficiency is really the key. And in our climate, and cold climates in general, it's to remember heating is our problem. And, do we really know our loads? Who really knows? It's kind of like in an off-grid home, you learn about your loads by needs. But in our normal everyday lives, as we go through and grow up, we have no idea where electricity goes. We turn on a TV, but we never think about how much is this actually consuming. We see the 1,000-watt sticker on a hairdryer, but we don't really understand what that means. How fast is that meter spinning when I use that hairdryer? And maybe I should just have it dry by the air in the house instead of using a hairdryer. So one of the first things I really recommend everybody as a general educational tool, and when you're on a quest of going off-grid, or even if you're on-grid and you're just trying to reduce your electrical loads, is figure out where your loads are. There's, for $20 you can buy a cheap meter which can measure your individual loads, or you can invest into a little bit more sophisticated system. There's a lot of these systems available nowadays. You can buy them for $200 on Amazon and install them on your main meter to figure out where are your loads really, and learn about electricity. In my opinion, there should be a big monitor somewhere in the house which tells you exactly how much are you actually using. We would be much more conscientious with the use of power if that would be the case. Like all of these lights we leave on, if we would see how much that actually consumes with a dollar sign trickling away, nobody wants to burn, free energy, and it's not free. We pay for it. It's expensive. In our town, it's 22 cents a kilowatt if we're on the grid, and if we're off grid, it's even more expensive because we have to produce it. So learn where your loads are. For our part, as professionals, as what we specialize in is high performance buildings. So I'm the nerdy guy who spends days and hours analyzing all of these loads when we design buildings. That's the only way we can make buildings 80 to 90% more efficient. We look at everything in this building, including insulation, windows, placement, orientation, all of the plug loads, all of the lighting loads, everything. And we use software programs, basically, which tell us the overall performance of this building, and allows us to basically tweak the dials on, well, maybe we need to switch out to a different refrigerator, or maybe we need to look at different options on our other plug loads. And we go down to phone chargers. We include everything which you have in your everyday life when we design these buildings, and it's fairly tedious and time consuming, but it's really the only way to get a true answer, which you like on this dashboard here. In a quick overview, we know exactly what this building will consume, and we can tweak it before we build it. And it's a lot easier to do this up front than later on. So, we have in the software all of these demands which we account for, all of the lighting, by light fixture. Usually we do a light fixture count by each room, by each light fixture. We look at what goes in there, how much is it consuming, and then we have an overall picture We look at a lighting cycle, we look at averages, and that's how we get our total number. And that's where we can see, you know, what our total power consumption is, which we need to design a renewable energy system for it. Or, you know, being able to certify, like this is passive house software. If we want to certify this building, we have to reach a certain energy target as far as primary energy goes. So we have to reduce the load tremendously. For a little bit easier and quicker calculations, you know, we have easier tools available, which don't take a degree to enter all of your loads to get a much broader overview. But in general, the thing to remember is, you know, you want to reduce your loads as much as you can up front, and you really need to plan for it. And in order to plan for it, you need to know what really is consuming what. So like lighting, if you're looking at lighting, a key example there, you know, it's not just about how many light fixtures are we putting in, but how do we place windows, and how do we use internal windows, like transom windows, like this here basically, for spaces where we don't have windows in the back rooms, where we can, you know, we have a cell-orientated building, since we want to gain maximum efficiency from passive solar gain. We have a lot of glazing in the south, but we don't want windows in the north because they're a complete loss in our climate as far as energy efficiency goes. But we need daylight, so we can, you know, utilize internal windows basically to bring that daylight back into the back of the building. And there's some really cool technologies which are out and about, especially in the commercial sector now, where we can tremendously reduce lighting loads just by daylighting, you know, where daylight is not just more energy efficient, it's a way more healthy and much better work and living environment. And then, you know, where we are technology-wise and cost-wise, LEDs are really the way to go, and especially on an off-grid building. There's just no way you want to go anything else because it's just so much more efficient. One of the big loads which we never really think about in our climate is clothes drying. You know, there's a tremendous amount of energy we waste with a normal clothes dryer. Think about it. You know, you take warm air which you have heated up in the building in the dead of winter, and you're exhausting it out. You're losing it, and it has to be replaced, and all just for drying your clothes. So not just that the energy required to run it is there, it's also the energy which you take out of the building and you exhaust out. So, I mean, what we in general really recommend, number one, use a clothesline. I mean, we've done that for thousands of years, and that works. You can just dry your clothes by hanging them up. That's what I do 99% of the time. It works great. It works very simple, and it doesn't cost anything. If you use a dryer in a high-efficient building or an off-grid application, I would closely look into a condensing dryer, basically. Condensing dryers are around for a long time. Bosch makes very good ones. That's what we usually install. There's other companies now who have them on the market. They're not much more expensive, but they basically use a condensate pump, and they don't exhaust out of the building. They just basically create a little bit of condensate, which goes right back down with the washing machine drain. So way more energy efficient, not just on the energy side from the electric, but also on the exhaust from the building, the warm air. You know, cooking choices, if you ask me what's the primary cooking choice for you to look at if you're trying to go off-grid, by far, in my opinion, it's wood. I would certainly have some means of cooking on a wood burning device if I would be off-grid. We've done that for hundreds of years, works great. We can integrate it really well in a masonry heater and some other custom-built ones, or they have some commercially ones available which work really well. And wood and propane are really the only sources you can get off-grid, which are, you know, not really energy hogs on your system. If you ask me on a grid-based system what to use for cooking, I would always tell you use an induction cooktop. They are by far the most energy efficient cooktop there is, but in an off-grid situation, that's just not the case, because we're really limited with our battery storage. With electricity is just too precious and too expensive. So different applications, different answers. And on an off-grid, I think wood and a high efficient wood burning device can make a really good combination to help on reducing your loads tremendously. And it also adds a complete different flavor to, you know, like the baking, and a wood-fired stove I think is way better than what you can achieve with just a regular modern cooking stove. Ventilation is one of the big things I talk a lot about, and which I think is completely underestimated. You know, unfortunately for us, in the dead of winter, most ventilation systems can't really work because it's too cold. You know, even if you have a heat recovery ventilator, a normal system, and it's very cold, just starts freezing up. So we're closing the outside air up and we go on a recirculation mode. We're not really delivering a lot of fresh air into the buildings. There's a lot of issues with fresh air in cold climates, and at 50 below, nobody opens a window to get fresh air. Very good, efficient buildings are airtight, and we're consuming the air in the building very fast. And so, without a mechanical ventilation system, we're creating a huge health hazard. And that, again, you know, that's nothing which kills you instantly. It just affects your health overall, and you are more sick, you're not feeling very well. And so ventilation, I think, is really crucial. And if we're looking at an off-grid situation where we're looking at really conserving as much energy as we can, it's even more important. So if we're looking at a load on basically just the overall efficiency of the building, with without an HRV versus with an HRV, it's a huge, tremendous difference. The peak heat load on the building without a really high efficient heat recovery ventilator is almost double. And that's because we're recovering 90% of the heat which we have in the building through the ventilation system. If you're just going on an exhaust only system, we're taking all of the heat which we made up with our precious fuel source, whatever it is, if it's wood, which we had to make, or if it is propane, or if it is fuel oil, or if it is electricity, whatever we use, we're using energy to make the heat for this building. And with ventilation, if it's exhaust only, we're taking that warm, precious air and we're removing it from the building. And we're starting on a baseline zero, and we're starting out from scratch. With heat recovery ventilation, we're combining basically the heat which leaves the building because it's used up. We're recovering that to these heat recovery cores, and we're conserving up to 90% of this energy, the heat, in the building. And if you're looking at this chart, you know, it's very obvious how much that is. And a lot of people don't seem to understand this. I just had a client again who we worked with for quite some time on some very interesting projects, and he's like, well, you know, we're really a little sticker shocked about a ventilation system, so on this next one, we just want to scrap it. And I'm like, well, but you're going to pay for it one way or the other. And I showed him the chart on what their annual, because I mean, this is in rural Alaska, and their energy costs are sky high. So the payback was within a year to really, if you look at the energy consumption, and that solved that question right away. But nevertheless, it's really something to remember. You know, if you don't have heat recovery, especially on an off-grid basis, you always have to start from scratch one with an exhaust-only system. We need to breathe. That's a fact, and it's very, very important for human health. Heat recovery ventilation is really, in my opinion, in our climate, a must for a good building. The reason we went for European units as far as the heat recovery ventilator is because they're just way more efficient. We are basically utilizing a ground-based small heat exchange loop which preheats the incoming air. That's this unit here, which instead of 50 below air hitting the HIV, we're usually hitting a constant of anywhere between 38 and 42 degrees. And we always can maintain ventilation at full capacity at 80 to 90% heat recovery. And these machines run at way lower energy requirements. It's 12 watts for the machine and 7 watts for the ground loop. So combined, the two machines still run lower than what you can buy, unfortunately, on the US market. I mean, heat recovery ventilation is really not, in our industry, not pushed forward good enough yet. The Europeans, with the higher utility costs for so much longer, have done leaps and bounds over the last 10 years in technology. So, you know, this is just a study we've done on the first one we installed in my house. It's a 2 to 3 degree differential at 49 below zero. It's tremendously how well these systems work, and the payback is, in my opinion at least, very, very good. Another one, a big one to remember, is the hot water in our buildings, and especially in an off-grid building. We're using a lot of energy every year in any building to make hot water, and that is really one of the big items to look at. How can we make that more efficient without using so much energy? So if you look at this chart, you know, the one which really stands out tremendously is hot water. This is a zero energy building we designed for dilutions, and so there is all electric. It's all powered by a wind turbine. That's why this is the domestic hot water with electric. But if you look at the loads, you know, I mean, this is a high performance passive house certifiable building. The domestic hot water by far is our biggest load. So, you know, water recycling, anything we can do to recover that amount of heat is where the low-hanging fruit is. And that, too, I want to point out again, you know, there's different technologies we can utilize. One creates hot water, basically a hot water-based system with solar. The other one, which Nathan explained in detail already, is recreating electricity. And each and every one has their own place and has their own efficiency. What are we trying to make and what are we trying to achieve is really the thing to always remember. There is no universal answer. So if we're looking just at the efficiency of the delivered energy from these panels, if we're trying to make heat, we shouldn't try to do this with a technology which is really not designed for it, because we have so many conversions which need to happen. And a thermal panel is very simple and very efficient at making heat, but that heat won't run the computer in the building. So somehow we have to have different technologies combined to do the right things most efficiently. You know, the hot water solar panel will produce a lot better domestic hot water than the solar PV will. And it will produce a lot better heating for a building than a PV system can do. However, it will never run any of the electrical requirements of the building. So we need both in a way. That said, you know, we hear this all the time, and I fight this for years. We don't have enough potential in Alaska for renewable energies. That's simply not true. This is my favorite comic. There's a ton of energy out there. It's free. We have a great potential in Fairbanks. We have in Fairbanks much higher solar irradiation than what you have in Germany with the most solar installations. We have 2 months in the wintertime where we have nothing. But for the rest of the year, if you're looking annually, we have a great potential here. We're very, very lucky that we have so much sun really overall. And I, at least on my quest on building high efficient buildings and living in a zero energy building, I have really learned how to love the sun. Like a day like yesterday, you know, it just makes me beam because I see all of this free energy I harvest all day long. That all said, thanks so much for coming out, listening to us, and hopefully you took a little bit of information away. There's a lot of good information on our webpage, arcticsunllc.com, or my other company, RENA, for the building portion of it. We're always open to talk to you guys if you have any questions. Take them outside if we don't cover everything here. Call us up, come by our shop. I mean, we're trying to make a living here, but we're also trying to really bring this community forward into a more sustainable north.
Way back in the middle of Nathan's slides, we talked about the lifespans of batteries and the performance batteries in the cold, stuff like that.
Mm-hmm.
And then immediately thereafter, there was a slide of monitoring devices. That brought me to the mental question. If I have a 24-volt battery system, and I'm looking at those charts, I'm trying to figure out where the zero number is. Is that truly 0 volts, or the 50%? Is that truly 12 volts?
That's a great question. So just like we said, 24 volt refers to when I say 24 volt, what that actually means is 12 battery cells. Each cell we call it 2 volt nominal. You're going to charge it at something other than 24 volt. If you have 0 volts, that's definitely super dead, I guess is how I describe it. That's beyond 100% discharge. That's like totally toast. So a good rule of thumb, and it's different chemistry to chemistry, but if you have a 24 volt system and your battery is at 24 volt exactly, that's about halfway discharged. And that's going to be plus or minus a little bit based on chemistry, but a 24 volt system that's fully charged, again, depending on chemistry, should rest up around 27 volts. 24 volt would be about halfway full. So, you know, and then it kind of drops off quick once you get deeper than that.
So if one were trying to figure out how to stay, say, in the top 30% of the battery usage, how would one find that number?
You got to go to your specific battery manufacturer. Every case is going to be a little different. There's some rule of thumbs, but it's really going to be based on the construction and chemistry of the individual battery. So if if you have a battery from a reputable manufacturer, they'll be able to supply that information to you. The other thing, I guess I didn't mention this. I kind of feel embarrassed not for mentioning it. Temperature has a lot to do with how you charge batteries too. So when I said 28 volt is a good charge for a 24 volt battery bank, well, that's true at a certain temperature, but as a battery gets colder, we need to charge it at a higher voltage to achieve the same state of charge. That, again, is something that can be supplied from a manufacturer, exactly what type of adjustments you can make. A good quality charge controller, be it from solar, wind, or a battery charger that's running off a generator, will automatically compensate for temperature, provided that you have a sensor on your battery. So if you buy a good quality charge controller, it'll come with a battery sensor. Don't skip it. It's really important. It does an important job. Yes?
What are the main factors that are standing in the way for hydrogen storage from photovoltaic?
I wish I had more to tell you. It's such an exciting field. It has such tremendous potential, and I just don't know. Do you know any more about it?
There's major corporations which don't agree with it. That's really, I think, the short answer. The technology has been around for this is around for a long time, and it has been successfully done not just by MIT but by other institutions too. Why don't we have it on the market? That's a very good question, but I don't have an answer.
I think one thing at least is safety issues with the storage. It's not like it's really, really volatile fuel source. I mean, properly contained, it can be totally safe, but it's what blew up the Hindenburg. So there's safety in storage is a prime concern that I will be looking at closely when a commercially available market does come online.
I have a fuel cell question. There are products on the market that are, I'm not sure what their fuel source is, whether it's pure hydrogen or like a natural gas base, but one of the waste products of that fuel cell is heat. Have you guys looked at harvesting the heat off of a fuel cell and the electricity off the fuel cell?
Again, great potential, and we as contractors, really, for the most part, look to what is commercially available, what has been tested through an authorized process such as UL testing. Legally, that's kind of what we get questions all the time about building your own solar panels. And we can probably sell you one for cheaper than you can build it for. And B, it's not really something we can do legally. The code requires that these products that we use go through UL testing. From that, I think there's an experimental side of our business where we are certainly pushing the envelope. But in terms of like working as a contractor, we're limited to the type of gear that we can really use to stuff that's gone through that rigorous testing. We're happy to answer any more questions out here. So thanks again for coming.